back to this week 10. We'll continue with our discussion on LLMs, but now with a focus on applying the techniques or the best practices that we learned about for classical ML earlier this course in the first few weeks regarding versioning, regarding CI/CD, regarding aspects related to testing. So we'll bring all those topics up now in the context of LLMs and see which one of those best practices still apply and how do you change, if we have to change at all, to suit the needs for LLMs. Let's start with versioning. So remember, there are two main artifacts here. One is the foundation model that gets produced at the end of the pre-training stage. The second is the fine-tuned model, which is task specific usually, which gets produced at the end of the fine-tuning stage. So the way you deal with each of these two is different. So if you look at foundation models, these are long-lived, they are multi-purpose, right? They get used in multiple different contexts by multiple different teams, potentially companies, individuals, etc. So the versioning that you need here is very similar to stable main branches that you see in Git repos, right? That's pretty much what you would expect because it's a common kind of a use. The data versioning here is something that you'll have to watch out for because the data versioning usually it's necessary to be multimodal. The data at the pre-training stage is a combination of text data, video, audio, binary images, etc., etc. As well as the data is going to be used for the LLM to be ready for multiple tasks, right? Which is speech recognition, image comprehension, etc. Whereas if you look at conventional approaches to data versioning, like even DVC as an example, the nature of change detection, because that change detection pretty much dictates how the we can quickly recognize which part of the data has changed so that we can keep track of it, right? It's usually dependent on modification time when the data was modified, files were modified, some kind of a checksum or a hash that's computed on the file, so that if the hash has changed, it means that something was modified inside the file, or the presence of new files, right, which is a new created time, which is beyond when you last ran a particular operation. Those kinds of methods don't really work very well for non-textual data, like for instance video data, audio data, image data, because in those cases small perturbations will result in significant rework. It's as though the entire image has changed. So data versioning has to be thought through carefully. In fact, my recommendation here is that tools like DVC might not be needed at all, because first and foremost, we're talking about massive data sets. Very few people are going to be able to have access to those kinds of data sets, and the job of running the pre-training itself is a massive exercise with a lot of planning and lineage and checkpointing and tracking, etc. So that itself gives you the traceability, provenance back to the data sources, and the data source curation process will help you hopefully create one clean version which is used for the entire exercise. So hopefully with that itself, or the combination of those things, you can get to the kind of data versioning that you need. So that's with respect to versioning of foundational models. Whereas with fine-tuned models, it's a completely different ballgame. Here, the fine-tuned models are model-centric, meaning that they are very specific to specific types of models that you build for specific tasks. Therefore, it makes sense to version every single such model. So you can do model-centric versioning. So it's kind of like how you would do with software or with classical ML. But with classical ML, we spoke about how the right approach might be to version the code, not the model. Only for large models, it makes sense to look at model versioning. So here, for fine-tuned models, we would most likely use model versioning, not code versioning, because these models are very large in size. So model-centric versioning is what we would recommend. Updated data is a critical artifact of how the fine-tuning keeps happening as a regular process. But the updated data is going to be incremental over and above the um, previous iteration. So remember that the pre-training data is very large. Foundation model gets produced, and then you're going to produce specific curated data for fine-tuning on top of that foundation model. That data set keeps getting updated. That's what we're talking about here, not updates to the foundation model's pre-trained data. So the fine-tuned data set keeps getting updated. So that is a regular data versioning exercise that you can do. So, but unlike the discussion that happened in weeks 3 or 4, you're not just versioning the code, you're versioning the entire model, including the lineage, so that you know the linkage between the updates to the data to the uh, through the code to the new fine-tuned model version that you're producing in that week. So if you take the example, there is a base model, usually like a foundation model. It's fine-tuned on week 1, fine-tuned on week 2, which is fine, and then you do some optimizations to make it more suitable, um, and then newer varieties, newer versions get produced. All of those result in variations of the models. So DVC, etc., continues to be useful here, no doubt about that. So in fact, if you go back and look at the recommendation we gave in this course, we said, why don't you go look at GitFlow as a very useful paradigm to follow for ML projects. So how do you adapt that GitFlow now to fine-tuned models? Remember that we're not going to do this for foundation, because foundation is a rarely done exercise, and it's a very special exercise outside the ambit of something that you would use GitFlow like automation for. But for fine-tuned models, there is a applicability. Firstly, artifact size. For if you use GitFlow for classical ML, the artifact sizes are in terms of code, right, which is megabytes. But if you start to adapt it to LLMs, the models themselves are large. So that's something to keep in mind. So here DVC plays a role. You use DVC to checkpoint the model, right, to do versioning of the model, and everything around the model, which is weights or everything else like hyperparameters, you go through the normal GitFlow process. So I should say Git repo, right? Um, Release cycles. So for GitFlow in classical ML goes through feature-driven releases, and then you can roll back to a stable branch or stable release. Whereas with LLMs, you have to do continuous, fine-tuning, right? So the retraining cost is heavy. So rollback might not be that cheap, right? Might be significantly expensive. Storage system, where do you store the Git repo, right? It can be local, it can be remote, but the code itself is in repo. Here, you'll have to use a combination of different stores. You might have the code obviously in Git repo, no doubt about that, but the models themselves might be in model registries instead of even DVC, right? And model registries have dedicated storage systems. So usually these are closely interlinked with cloud. Branching, the GitFlow recommendation is, bugs have a separate branch. You finish the branch development, the testing, regressions, and everything, and then you merge it back. Likewise for features. Here, there are extra branches which are possible based on dataset updates, based on new experiments that you want to do, like for instance, distillation or quantization experiments. LoRa, as an example, is one such algorithm that you can use. So each of those become experiments, and then those experiments are their own branches, and the branches go through their own life cycle. Version tags are usually attached to every release, whereas here you might want to attach semantic model tags, not just versions for the release. So it's useful for you to then track which tag pertains to which model. Rollback strategy. So you can easily do a rollback by just going back to a specific branch. GitFlow allows that. Like the branch has a specific release, so the release allows you to go back to, rather I should say, release has a specific branch, so you can go back to a particular release by checking out that branch and promoting that to deployment. So here you've got to do a bit of the checkpoint management yourself, right? Sometimes you might have to do a full redeployment, and which is still okay because you can still use GitFlow for different experiments or different dataset based fine-tuned model changes, and then use the full redeployment of that particular branch. And last but not the least, governance, code reviews, CI meaning testing, the use of CML that we did. All of that is fine. All of that is required for LLMs. On top of it, you will still need human in the loop audits for things like bias checking, testing, etc. Or even data set tracking. So that's how the GitFlow process gets adapted. So as you can see, most of the methods or techniques are still the same. There are some additional adaptations, and then there are a couple of variances, like for instance for data versioning, or rather the model versioning itself is something that you'll have to do for LLMs. Okay, let's spend a bit of time talking about testing. Testing is a very interesting topic when it comes to LLMs, because unlike software testing, which is deterministic, where you can provide outputs that you're expecting and have the software consistently produce the same output if it's running correctly, and then compare the two outputs and say that the software is right or wrong. With LLMs, due to the inherent noise in the entire foundational architecture of these LLMs, you're never going to get the same answer consistently. You might get it once or twice, but even the third or fourth time, you're going to start seeing variances. How do you then test LLMs? In fact, the broader qualitative question is, how do you test creativity? Because ultimately LLMs are predicting the next token, and they go through various branches which are possible, starting from one choice that they have, and ultimately they're trying to produce answer that meets the bar for a question, but they have different ways of trying to get to answers. So in a sense, that's like the creative thinking process that a human goes through. So how do you then test it, right? You can test for usefulness, maybe, right? And that comes down to creating the right rubric for controlling what goes in, what comes out, the extent of what's coming out, right, etc., etc. Let's talk about that a bit. So one, you can of course test for data validation. You should, meaning every time you're going to use data for fine-tuned models, test it, right? Make sure the data is of good quality, has got the right profile, there is no drift, right, etc. You can also do model performance tests, right? And here you can measure accuracy by comparing known results with what the LLM is producing for factual data, for numerically correct data, not for qualitative questions or qualitative prompts, but things which are known, things which the model did well last time around. So that brings us to the point of regression tests, right? That's something that's very, very important. So one anecdote I want to share here is, there was this incident with I think GPT-3, if I remember right, or GPT 3.5 Turbo. When it was first released as a first version, OpenAI had announced some new capabilities, like for instance code generation and a couple of other things, math reasoning, if I remember right. So that was, it showed some amazing capabilities, and that opened up the eyes of people, right, because of the kind of capabilities, kind of things that you can do with a chat GPT or GPT. And then they released another version within 3 months or 6 months. Again, there was a big announcement about the capabilities of that model. But what ended up happening was, for critical tasks that they announced with much fanfare before, like math reasoning, code generation, etc., the same class of models now performed poorly, right? It kind of regressed on the performance of what the previous version was able to do. Nobody knows why, right? Because OpenAI itself didn't admit it per se. It was just something that academically or usage-wise people were noticing anecdotally, and they pointed this out on Twitter, and then OpenAI maybe quickly arrested it and released a different version. But the point being, there was no regression tests on the benchmarks that they tom-tommed about, right, in the previous release, and that was quite a glaring gap. So these are things that you do normally. There is no magic to it. You just do it for LLMs as well. The harder things to do are around hallucination, consistency, toxicity screening, right? And in many cases, you might also require to do all of this online, right? So testing as part of the CI cycle is when the fine-tuned model is getting produced and the fine-tuned model gets certified for production usage. Unlike software, which is deterministic, which produces the same thing in testing, which will also produce the same thing in production, LLMs are not giving that guarantee, right? So you might test for hallucination, you might test for consistency and toxicity screening at the point of CI, right? So that the fine-tuned model then gets certified to be shipped out. But once it's shipped out and once it's used in production, at that time it might start hallucinating because of the way the prompts are engineered, the way the customer is guiding it, right? How do you then test it for the hallucination that's happening there? Because ultimately, what do tests capture? They capture the guarantee that the software is working as advertised, which means if the software is not working in production, it fails this guarantee. The fact that it's not working in production because of inherent variability, inherent non-determinism that LLMs have is not something that the end user is going to give a damn about, right? Or is going to worry about. So it's up to us as developers of fine-tuned models, not only to test it in CI stages, but also to test it in production in an online manner. As and when the responses are being given out, you'll need to have a appropriate screening check for it, for hallucinations, for toxicity, etc., etc. So we'll talk about how um, the architecture can be set up in the next week's lectures. So ultimately, like ML, LLM fine-tuning is not a done and dusted approach. So CI/CD is like an absolute must. Let's take a look at specific testing that we could extrapolate from what we've already seen with software and classical MLOps. So unit tests, of course, classical ML need it. We saw examples of it earlier. Here in LLMs also, when you fine-tune it and build a fine-tuned model, you would need it. And on top of the typical unit tests that you'll see for code, you'll also need tests for prompt templating, whether the prompt templates are happening correctly, whether there is scope for improvement. Like for instance, one of the common ways in which you bound the context within which the LLM is going to answer questions or prompts is to take on the role of a specific individual or to uh, or to be provided guidance and rules within which it has to think. Like for instance, if I use let's say a GPT and I use it for preparing for a speech on a stage, then I'll give it that context that, hey, I'm going to talk on stage for a couple of hours to an audience of 100 people. So guide me in my English formal language, right? So that's the prompt template I'm going to provide, and within which I'm going to give various topics I'm interested in developing new content for, and then GPT will come back with answers for it. So prompt templating is a critical aspect that you could test out as at the unit level. Likewise, tokenization as well. Are you chunking the text properly when a prompt is given to you, etc.? Data tests, obviously, super important because we want to do also things like bias detection and hallucination prevention, etc. So you've got to put the right types of checks for ensuring biases don't exist or it's balanced, underrepresentation, overrepresentation, those kinds of issues are not there, and also things like uh, uh, data quality, etc. So those kinds of checks can also be there. Performance tests are important. That's what allows you to certify that the model is good to go. Accuracy, F1, recall, those kinds of matrices. Here, apart from those matrices, which you can still compute, by the way, for LLMs with known data sets, right? So you can say, for instance, rather a factual question, if it gives back a factual answer, great, right? You can directly compare and say, it matches your template answer, it doesn't match your template answer. So you can give like an accuracy metric 0 or 1. But you also need to do more testing for things like toxicity screening, consistency, etc. So there you've got to ask the same question multiple times, for instance, or you got to intentionally provoke the LLM with a potentially toxic question and see what it comes up with. So those kinds of tests are also there. Model performance tests are also there. Drift tests are super important because drift basically is a common problem. Classical ML, yes. Here also, you've got to understand drift in the data that's there, but you've got to also understand the semantic drift that's possible in the responses. And that's something that's, something that you can write tests for. Security tests are rare in classical ML. It's there for to a limited extent. In LLM's case, it's very essential because the type of security threats which are possible with open languages is significantly more. The attack surface is significantly more than structured languages where you can put, very strong security principles around. So that's one type of testing which is, in fact, in my view, it's an emerging field. There's a lot of work to be done here. Qualitative tests are also essential. So here we're talking about helpfulness. Is the output meeting the bar with respect to at least trying to answer the question? So if I'm asking insurance chatbot, which is trying to help me with customer service requests, hey, is diabetes covered in the policy? I don't want it to come back and say your in-room rent is 20% more expensive if you go to an out-of-network um, hospital. The answer is absolutely no meaning at all, right? It meets the bar for toxicity screening. It meets the bar for bias. It looks like genuine English, but absolutely useless for the question I'm asking. So helpfulness is a critical aspect. Safety is a critical aspect. Is it giving wrong instruction, which is resulting in potentially dangerous outcomes? So those are things that you'll have to watch out for. For some of these tests, automation might not be the full answer. You might have to have human involved in the feedback loop. Okay, so I'll take a pause here. In the next video, we'll talk about the actual CI/CD practices themselves.